So, we will start with a simplified circuit where I have a converter with 3 legs. And in each leg there are 2 thyristor valves. So, there are 3 legs shown here, and in each leg we say there are 2 thyristor valves. So, say there are 2 ways of saying. One is one can say that a converter consists of 2 basic commutation groups connected in series, or there are 3 legs, which is the usual term used in many books, 3 legs connected in parallel. So, there is 1 leg corresponding to each face of the AC side. So, we denote the 3 phases by the letters A, B, C. So, I have on the AC side a balanced 3 phase voltage source, so let me call this voltage EA, this voltage is EB, and this is EC. So, the valves are numbered as 1, 3, 5, 4, 6, 2. On the DC side, the representation is a current source which is constant. So, I have a constant current ID on the DC side. The voltage across the DC side terminals is VD. So, this is the simplest circuit where I have actually ignored the inductance on the AC side. So, let us try to analyze this. So, we saw that in the last class I can divide the converter into 2 basic commutation groups, upper commutation group and a lower commutation group. 135 form the upper commutation group, 462 valves form the lower commutation group. Now, at any instant only one thyristor valve in any commutation group conducts, that is 1 among 135 and 1 among 462. Okay. Now, for the sake of simplicity, what we will do is we will assume that gate currents are continuously given. Okay. So, if gate currents are continuously given, it is as good as thyristors acting as diodes. Okay. So, if I say gate current is continuously applied, this is as good as saying that thyristor behaves as a diode. So, behaving as a diode means if it is forward biased it conducts, if it is reverse biased it stops conducting. Okay. Okay. Now, the question is, in any commutation group 135 or 462, which is the thyristor valve that conducts? Suppose I take the commutation group 135. So, how do we decide which one of the 3 valves 135 conducts at any time? If you notice, the cathodes of all these thyristor valves 135 are at the same potential. So, the one that conducts is the one with which has the highest potential for the anode. Similarly, if you take the lower commutation group 4, 6 and 2, the anodes are at the same potential. So, the one that conducts is the one which is having the least cathode potential. Okay. So, that is the idea. Okay. So, of course, one has to note that, I mean, of course, one can verify when one of the thyristors valves, one of the thyristor valves is conducting, the other 2 thyristor valves are reverse biased. Okay. So, that we will verify. Okay. So, we will assume some expression for this EA, EB, EC. So, I said they are balanced sinusoidal, that means they are having the same RMS value or peak value, and the phase angle difference between EA and EB or EB and EC or EC and EA is 120 degrees. Okay. So, let me assume some expression for EA, EB, EC. Now, the only choice I have is assuming the absolute phase angle. I have no choice over the relative phase angle. So, any two voltages will have a phase shift or phase difference of 120 degrees. So, I will use this expression root 2 by 3 V sin omega O t plus I will choose an angle 150 degrees. I could have chosen any angle instead of 150. I mean, any arbitrary angle can be chosen, but I am choosing 150 for some reason. It's a bit convenient for me, as we will see. Okay. So, V is a constant, omega O is a constant. So, it's a sinusoidal waveform. So, what is this V? So, if I say this is the expression for EA, what is V? RMS value of line to line voltage. So, please note the 3 voltages EA, EB, EC, the 3 voltage sources, single phase voltage sources are connected in Y or star. So, if you look at the line to line voltage, it has an RMS value V. Okay. So, that is EA. So, once I have EA, I choose I mean, I have no, of course, I have no choice over EB. It has the same RMS or peak value, and it lags EA by 120 degrees. So, this is sin omega O t plus 30 degrees, and EC lags EB by 120 degrees. So, it is root 2 by 3 V sin omega O t minus 90 degrees. Okay. So, let me try to draw the waveform of EA, EB and EC. Suppose so, this is EB. Is the yellow line visible? Okay. Then EC lags EB by 120 degrees. Okay. So, since it is freehand drawing, please note all these waveforms are sinusoidal waveforms, though it may not slightly appear like that, and they are balanced. That means they have equal equal peak values. So, this is EC. Okay. So, I will mark some angles on the abscissa. So, if I try to take this instant as 0, the instant at which EA and EB are positive and equal in value. Okay. So, what will be the instant at which EA is having a 0 crossing from negative to positive? please note our expression for A is this, it is root 2 by 3 V sin omega OT plus 150. Okay. So, this will be minus 150. So, what I have shown is every 60 degrees. So, this is minus 90 degrees, this is minus 30, this is plus 30, this is 90, 150, 210, 270 and 330. So, I have shown every 60 degrees, only only thing is I have showed an additional instant 0 also. Okay. Now, just now we saw that if I look at the commutation group consisting of valves 1, 3, 5, at any instant the valve with the highest anode potential conducts. So, let us try to see, or let us try to first mark the instants of the conduction of different valves based on the one with the highest anode potential. So, if I take this instant, okay. So, if I take this instant and if I take this instant, now from this instant to this instant, can I say one of the thyristor valves in the upper commutation group has the highest anode potential? Among 135, which one has the highest anode potential? 1. Okay. So, it is 1. Similarly, from here to here, from this instant to this instant, one of the thyristor valves among 135 has the highest anode potential, that is 3. And again from this instant to this instant, the thyristor valve 5 is at the highest potential. Okay. So, now we know which one among the thyristor valves of the upper commutation group conducts. So, if you have noticed, we have considered one full cycle 360 degrees. See, we started from minus, though I have not marked, it is minus 120, and we go up to, I have not again marked here, between 210 and 270 there is a 240. So, minus 120 to 240. So, for one full cycle 360 degrees of the AC side, we have noted which thyristor valve of the upper commutation group conducts. Now, we have to also find out which one among the lower commutation groups conducts. Okay. So, I will just extend these lines. So, this is corresponding to 1, this is corresponding to 3, and this duration is corresponding to 5. Okay. Now, to find out which one among the lower commutation group conducts, I take this instant and this instant. Okay. Suppose I take the duration, though I have not marked, minus 60 to plus 60, minus 60 to plus 60. So, from this point to this point. So, there is one thyristor valve which is at the least cathode potential. Which one is that? From here to here. Sorry? Yeah, please go to the circuit 462. Which one among these? 2. So, it is 2. Again, from 60 degrees to 180 degrees. So, for this duration, one of the thyristor valves is at the least cathode potential, 4, and from 180 degrees to 300 degrees, it is 6. Now, though I have not shown for the duration up to 60 degrees, up to minus 60 degrees. So, if I take this duration, again this is of 120 degree width, but I am not showing the entire duration. So, if I take for this duration which is up to minus 60 degrees, which thyristor valve is conducting? 6. Okay. Now, again I have covered one cycle. See, if you look at the durations for which either 2, 4 or 6 conducts, I mean the total duration is 360 degrees. Now, what we will do is we will try to consider intervals of length 60 degrees. Suppose I take this or this or this, all these are intervals of duration 60 degrees. Okay. So, at any instant, one thyristor valve in the upper commutation group conducts, one thyristor valve in the lower commutation group conducts. So, in the first 60 degree interval, it is 1 and 6. Okay. So, instead of writing 1 and 6, I say 6 and 1, 6 comma 1. Then in the second interval of 60 degree duration, it is 1 and 2. Then it is 2 and 3. Then it is 3 and 4. Then it is 4 and 5. Then it is 5 and 6. Now, that actually completes one cycle. So, if you go to the next interval, it is corresponding to the next cycle. Again, this same sequence follows. Okay. Now, what we have done here is, first of all, we should note that we have assumed that the thyristors are acting as diodes. So, continuous gate current is applied. So, thyristors are acting as diodes. So, we will go to the general case of thyristors are acting for as devices for which they are used. Okay. Say, obviously, if I use thyristor, I invest more money than that I do for the diode, and obviously it is used for control purpose. Okay. So, there is a provision to delay the instant of giving the gate pulse. So, actually gate current is not continuously applied, gate current pulse is given, so that I can delay the instant of turn on, so that I get some control over some quantity. Okay. So, essentially I can get control over, say, the DC voltage. For a given AC voltage, I can get control over the average value of the DC side voltage. Okay. Now, we define one thing which is called instant of natural conduction. Now, this is a quantity which is defined for any valve, any of the 6 valves. So, instant of natural conduction of a valve. So, what is this instant of natural conduction of a valve? It means the instant at which the valve starts conducting if the gate current is continuously applied. So, that is the definition. So, this is instant of or instant at which. So, please note this is defined for each and every valve, all the 6 valves. So, if I take one particular valve, the instant of natural conduction of that valve is nothing but the instant at which the valve starts conducting. Instant at which the valve starts conducting, provided I give continuous gate current. Okay. So, if gate current is continuously applied. So, that is the definition of instant of natural conduction of a valve. Okay. Let us say for one of the valves, what is the instant of natural conduction? Suppose I take the instant of natural conduction of, say, valve 3. See, I mean the independent variable is normally the angle omega OT. So, though we say instant, we refer to even omega OT as well. Okay. So, omega OT is equal to 0. So, you see that at omega OT equal to 0, 3 starts conducting. So, the instant at which 3 starts conducting is omega OT equal to 0. Now, this is the instant at which it starts conducting if gate current is continuously applied. Okay. So, what we do in practice is instead of continuous gate current pulses are actually applied which are delayed by a certain angle. Say it is as good as applying, say there is one more equivalence. Instead of continuous gate current, diode operation is possible even if I just apply gate pulse at the right instant. So, in the case of valve 3, if I apply the gate pulse at omega OT equal to 0 and the next gate pulse for the same valve for the same valve, I am talking about the same valve 360 degrees. See, you apply gate pulse only once in one cycle. So, say there is a diode operation possible even with gate pulse. If I apply gate pulse to valve 3 at omega OT equal to 0, 360, 720 and all multiples of 360. Okay. So, similarly for each valve, instead of giving continuous gate current, I can apply gate pulses every 360 degrees at the appropriate instant to get diode operation. Okay. So, what is actually done is neither continuous gate current nor gate pulse to achieve diode operation. Okay. So, we want to have control. So, what we do is instead of continuous gate current, what is actually done is gate current pulses are applied which are delayed by an angle. So, which are delayed by an angle. So, we give a notation for this angle alpha. Now, this delay is measured with respect to the instant of natural conduction. Okay. So, by an angle alpha with respect to the instants of natural conduction. So, for this converter there are 6 thyristor valves. So, that means there are 6 instants of natural conduction. Now, for each thyristor valve we delay the instant of gate current pulse by the same angle. Please note this alpha is not different for different valves. So, alpha is same for all the valves. Okay. For all the 6 valves the delay is same. Okay. So, that is denoted by alpha. So, there is a name for this, I mean alpha is called delay angle. So, for example, if I take valve 3 for example, if I take valve 3 is turned on, that means a gate current pulse is given at. So, if the delay angle is alpha, what is the instant of the gate current pulse or the instant of turn on for valve 3? See, what was the instant for natural conduction for valve 3? 0. So, this will be I mean the instant of turn on in general is omega OT equal to alpha. See, if you take valve 4, what is the instant of natural conduction for valve 4? 60 degrees. 60 degrees. So, the valve 4 is turned on at 60 plus alpha. The instant of natural conduction for valve 5 is 120. So, valve 5 is turned on at 120 plus alpha, so on. Okay, okay. So, for valve 3 it is alpha, just alpha. Okay. So, what happens to the valve which was conducting earlier? Say valve 3 is turned on at omega OT equal to alpha. What was the valve that was conducting before valve 3 is turned on? Which valve was conducting? Valve 1. So, what happens to that? That will turn off, it gets reverse biased. So, it gets reverse biased and it turns off. Now, this is irrespective of whether I give continuous gate current or gate pulse, it is irrespective of that. Say initially I considered continuous gate current, I mean to explain the operation, that was operation as if everything is I mean all valves are working as diodes. So, irrespective of continuous gate current or gate pulses, as soon as valve 3 is turned on and it starts conducting, valve 1 will turn off, and of course, one can verify that it is reverse biased. Is it not reverse biased? What will be the voltage across valve 1 as soon as valve 3 is turned on? EB minus EA. So, what happens to EB minus EA?
Actually, anode to cathode will be A minus EB. A minus
Yeah.
EB will be negative.
Say we define one quantity here for convenience, voltage across a valve. Voltage across a valve, whether it is valve 1, 2, 3, 4, 5 or 6. By definition, it is the potential of anode. So, every time I will not say the potential of anode with respect to cathode. So, I will just say voltage across valve 1, potential of anode with respect to cathode. Of the valve. So, I was asking what happens to the voltage across valve 1 when valve 3 is turned on. Okay, let us find out the expression for voltage. Okay, so when valve 3 is turned on at omega OT equal to alpha, turned on at omega OT equal to alpha, then the voltage across valve 1, voltage across valve 1 is equal to. So, let us go back to the figure, the circuit diagram. So, 3 is turned on. So, 3 is turned on means the valve 3 acts as a short circuit. So, we are assuming ideal thyristors. So, the voltage across the thyristor or thyristor valve is 0 when it is on or when it is conducting. Okay. So, this is a short, valve 3 is a short. So, what is the voltage across valve 1? It is anode potential minus cathode potential. So, it is EA minus EB. So, it is EA minus EB, which can be obtained from the circuit diagram, EA minus EB. Now, we have expressions for EA and EB. Now, using the expressions for EA and EB, can I say what is EA minus EB? EA is having a phase angle 150, EB is having a phase angle of 30. Root 2. First of all, this is a line voltage. Please note EA minus EB is a line voltage. So, the peak value is root 2 V sin omega OT 180. So, can I say that it is minus root 2 V sin omega OT? Okay. Now, for the time being, let us assume that alpha is taking such a value that voltage across valve 1 is actually negative as soon as it stops conducting. Okay. So, then what should be the range of alpha? Say alpha can be 0, say alpha is equal to 0 corresponds to diode operation. Now, if alpha is increased, okay. Now, beyond a certain value, what happens to voltage across valve 1? See, please note this voltage across valve 1 is negative only for omega OT less than, look at the expression, minus root 2 V sin omega OT, it is negative only from 0 to pi by 2, is it pi by 2? 0 to
0 to pi.
0 to pi. Okay. So, for the time being we will assume that alpha is close to 0. Okay. We will consider the general case shortly. So, if alpha is say close to 0, okay. So, then as soon as valve 3 is turned on, voltage across valve 1 is negative as soon as it stops conducting. Okay. Now, actually that is a mandatory requirement, because if the voltage across valve 1 is not equal to a negative value for a certain minimum duration, then it will again start conducting without gate pulse.
Yes, because the current is not.
So, that is a property of the thyristor. I will not get into the device physics here. So, I mean, I do not know whether you are familiar with that. A thyristor will actually start conducting again. See, the thyristor, once it stops conducting, because current goes to 0. Okay. So, if it current goes to 0, it starts conducting. Sorry, current goes to 0, it stops conducting. Then as soon as it stops conducting, the voltage across the thyristor should be negative, that is anode to cathode voltage should be negative. If it becomes positive, it is forward biased, and without gate current it will start conducting if it is not negative for a certain minimum duration. Okay. So, that is one property of thyristor which we have to consider in this course. Of course, in the analysis of any converter, though we are assuming ideal thyristors. See, please note, in other ways it is ideal, but as far as this aspect is concerned, we have to take that practical operation of thyristor here. So, there is a certain minimum duration. See, we do not want the thyristor to conduct as soon as it is forward biased. We want the thyristor to conduct when we want, that is when we give the gate current pulse. So, if it conducts just because it is forward biased, then the control is lost. Okay. So, whenever a thyristor valve stops conducting, then there is a minimum duration for which the voltage across the thyristor valve should be negative. If that is not maintained, if it again becomes positive, the thyristor starts conducting again without gate pulse. Okay. So, this is something we will come back again. Okay. So, we will come back to that analysis again. Now, what we will do is, we will try to look at the different intervals that we have seen in the previous page. Say there are 6 intervals in one cycle, each interval is of duration 60 degrees. Okay. So, we will try to form a table and do further analysis. So, I will list all the 6 intervals, and in each interval we will see what are the valves. There are 2 valves, one valve from the upper commutation group, one valve from the lower commutation group that conducts. So, valves that conduct, and we are interested in what is happening to the DC side voltage. Okay. So, we will look at the expression for the DC side voltage Vd. See, Vd is, if you go back to the circuit, Vd is the voltage across the DC side terminals. Okay. So, we look at the expression for Vd, and we will also look at voltage across one of the valves. There are 6 valves. Now, one can show that there is symmetry. If you look at the voltage across one of the valves, say valve 1, the voltage across valve 2 will be similar to valve 1, in fact identical to valve 1 except for a phase shift. So, voltage across all the valves are identical except for phase shifts. Okay. So, I can just see what is happening to voltage across one of the valves. So, voltage across say valve 1. So, I will try to form a table. So, there are 6 rows in this table. So, the 6 rows corresponds to the 6 intervals. Okay. So, what is the first interval? Okay, I am not going by this figure. See, this figure has 6 intervals, but this was corresponding to diode operation. See, please note here, this is something which is corresponding to continuous gate current. Okay. So, if I assume a general case where there is a delay, okay, if there is a delay in giving a gate current pulse with respect to instant of natural conduction, what is the first interval? See, suppose I take valve 3, valve 3 is turned on at alpha. Okay. Now, it continues to be on up to what instant? Alpha plus 120. So, each thyristor valve conducts for 120. Okay. But before the next thyristor in the same commutation group starts conducting, there is one more thyristor valve in the other commutation group which starts conducting, that is 4. See, 3 is in the upper commutation group, 4 is in the lower commutation group. So, 4 is turned on at, see, you can refer to this figure where I have considered a continuous gate current. So, at 60 plus alpha. So, here the only thing is the gate pulses are as good, it is as good as giving gate pulse at 0 for valve 3, at 60 for valve 4 and so on. Now, in general it is alpha for valve 3, alpha plus 60 for valve 4, alpha plus 120 for valve 5 and so on. Okay. So, I can say that I can consider the cycle which is of duration 360 degree to be divided into 6 equal parts. So, each of these is called an interval. So, the first interval is between alpha and alpha plus 60 degrees. Okay. Then the second interval is between alpha plus 60 degree. See, what I have written here is, in the first case, omega OT is greater than alpha and less than alpha plus 60. Then the third interval is alpha plus 120 to alpha plus 180 degrees, then alpha plus 180 degrees to alpha plus 240 degrees, alpha plus 240 degrees to alpha plus 300 degrees. And the last interval is alpha plus 300 degrees to alpha plus 360 degrees. Okay. Okay. So, we have just listed all the 6 intervals in one full cycle. See, this one cycle is for the AC side. Our AC side period is 360 degrees, please note that. Okay. So, if I take the first interval alpha to alpha plus 60, what are the valves that conduct? Valve 3 is turned on at alpha. So, there is one more valve in the lower commutation groups that is conducting, that is 2. So, valves that conduct in the first interval are 2 and 3. Then the next interval 3 4, 4 5, 5 6, 6 1, 1 2. Then if you take the next interval, of course the cycle repeats. Now, can I write the expression for VD in terms of, say, EA, EB, EC, looking at the circuit diagram? See, in the first interval 2 and 3 are conducting. So, if you look at the circuit diagram, from the circuit diagram, if 2 and 3 are conducting, can I get an expression for VD? See, it is as good as saying 2 is a short circuit, valve 2 is acting as a short circuit, valve 3 is acting as a short circuit, other valves are open, acting as open circuits. So, the positive terminal of the DC side is connected to the positive terminal of EB through this valve 3 which is acting as a short circuit. See, what I am trying to say is, in the first interval 2 and 3 are conducting. So, they are acting as short circuit. So, the positive terminal of the DC side is connected to the positive terminal of EB, the voltage source EB through valve 3. The negative terminal of the DC side is connected to the negative terminal, positive terminal of EZ through valve 2 which is again acting as short circuit. So, what is VD? EB minus EC. Okay. So, it is EB minus EC. So, let us write that. So, EB minus EC. So, looking at the circuit diagram, we can say what is the expression for VD, because based on what are the thyristor valves that conduct, I mean they are acting as short circuit. So, you can easily get the expression for VD in terms of EA, EB and EC. So, when 3 and 4 conduct, EB minus EA. So, the valves that conduct are actually acting as short circuits. So, when 4 and 5 conduct, EC minus EA. When 5 and 6 conduct, EC minus EB. Fine. Then when 6 and 1 conduct, EA minus EB. When 1 and 2 conduct, EA minus EC. Fine. This can be easily obtained from the circuit diagram. Then let us look at the voltage across one of the valves, say valve 1. Now, how to get the voltage across valve 1? Again, go back to the circuit diagram. So, 2 and 3 are conducting in the first interval. So, what is the voltage across valve 1? Now, it does not matter whether 2 conducts, the point is 3 is conducting. So, once I know 3 is conducting, 3 is acting as a short circuit, and the cathode of valve 1 is connected to the positive terminal of the voltage source EB, and the anode of valve 1 is connected to the positive terminal of EA. So, from that I can say what is the voltage across valve 1. So, it is EA minus EB. Yeah. So, I will stick to the definition of voltage across a valve. It is always the voltage of the anode with respect to the cathode. Fine. Similarly, can we say what is the voltage across valve 1 when 3 and 4 conduct? Again, go back to the circuit diagram. Now, it does not matter whether 4 conducts or not, 3 is conducting. So, it was the same as what happened in the previous interval. So, whenever 3 is conducting, it means it is EA minus EB. Now, in the next interval, 4 and 5 conducts. So, please note again, it does not matter whether 4 conducts or not, 5 is conducting. What matters is 5 is conducting. So, since 5 is conducting, 5 is acting as a short circuit. So, voltage across valve 1 is EA minus EC. Again, in the next interval, it does not matter whether 6 conducts or not. Say whether 4 conducts or 6 conducts, it does not matter. The point is 5 is conducting. So, the expression is EA minus EC. And the last 2 cases are very easy. So, in the next 2 intervals, 1 is conducting. So, 1 is conducting means by our assumption of ideal thyristor valve, this voltage is 0. So, we will try to analyze further by using this table and a few other explanations that were done in this class. So, I will continue this in the next class.